Good afternoon, everyone. Welcome to our pre-lab lecture. Today's experiment is on molarity and solution. First, I'll walk you through the data sheet on how to complete the data sheet before we take the quiz for this lab. As I said, the experiment is on molarity and solution. It turns out that the molarity, all right, molarity is a unit of measuring concentration of solution. Okay, concentration of solution. And when we talk about solution, it's made up of two things. That is the solute and the solvent. In solution, the solvent is present in large amount and the solute is present in a small amount. Solvent large amount and solute small amount. It's not necessarily that solution are made up of liquid and solid substances. You can have gases, solution being homogeneous, and you can also have solid solution, such as in alloy. All right. Yes, I'll talk about that. Margaret, I'll go through the data sheet. Each and every item on the data sheet I'll go through. I want just to go through some of the terminologies you will encounter when you will be completing the data sheet. So let's start off with the first solution. It is solution is made up of solute and solvent. These are the key terms you should be familiar. Solute is always present in some small amount, and solvent is present in large amount. Uh, there is a term here we will also use, and there is the mole. Mole is a unit used by chemists to express certain number of items such as atoms or molecules. And if you have the Avogadro number of items, you talk about the mole. I don't want to go in details into Avogadro number mole, but the relationship between mole and molarity has to do with how we calculate the molarity of solution. Let's see if I can share my screen here. My I want to use my iPad as whiteboard. All right. I want to use my iPad as whiteboard. In this case, allow me to sync and have a new page on my whiteboard. Hopefully it's gonna load a new page for my iPad so that we can look at. Yes, so this is the whiteboard, and molarity is simply determined by taking the number of moles. All right, I talk about the moles, which is represented by Avogadro number over volume in what? Volume in liters of solution, volume in liters of solution. So if you have a solid, all right, if you have a solid, you dissolve and you dissolve the solid and adjust the volume to any given amount and change that volume to liters. Number of moles over volume in liters gives you the molarity of solution. You'll see this equation, M for molarity equals to number of moles of solute over volume in liters of solution. milliliters of solution. The top part, okay, for our experiment, the top part, this number of moles, you'll have to calculate. Number of moles is given by this equation. If you know the mass in grams, that is mass in grams of solute, all right, mass of solute of the molar, molar what? Molar mass. Molar mass, you can use the periodic table. This is from the periodic what? Use periodic table to find the molar mass. You know how to use the periodic table, right? Given the chemical formula, you should be able to calculate the molar mass of compound. And I believe this is double check. This is the uh, this is the chemical formula for the compound we are going to use today. All right. Chemical formula we are going to use today. I guess the my whiteboard is not working, so I'm gonna try the annotation. I'll try the annotation. C, cobalt, slow, chloride, uh, uh, copper sulfate. All right, copper sulfate, SO4, like that, copper sulfate, copper 2 sulfate. This is Cu dot, there is a dot here, 6 H, all right, H 2 O, H 2O. This is copper 2 sulfate hexahydrate. We are going to use this as our solvent. And if we don't know the chemical formula, all right, it's gonna be hard to get the what? To get the molar mass of the compound. So how are you going to do that? Some student I see quite often is they think that this is multiplication. This is not multiplication. It means you have to find the molar mass of H2O, which you should know, 18.02 times 6. And then you're going to add the molar mass of the ionic compound part of this hexahydrate. You see this? So I'll find the molar mass of this part, find the molar mass of H2O times 6, and then add the two. It will give you the mass or molar mass of the compound you will be working. So concept of finding the molar mass of a compound given the chemical formula is something you should have learned before this point, okay? Before getting here. So it's assumed that you know, and I've given you a hint how to find the molar mass of the compound you'll be working with. So that is this is one of the equations you will be using molarity. We'll be using molarity. All right, and let me just exit this. Just gonna get rid of the molarity. Now, we will also, all right, we will also use another equation for determining the concentration of solution, and this is the dilution law. Dilution law here is just taking the, all right, taking the concentrated solution and lowering its solution. We use this equation, all right, for dilution law. Dilution law, we use M1, all right, you know M1, V1 equals to M2, M2 V2 for volume 2, volume 1. This is called dilution what? Dilution, dilution is hard to write on with a mouse. Dilution what? This is dilution low, dilution low. We use to bring down a concentrated. Sometimes this is MC for concentrated, VC for concentrated. In this equation, all right, notice that we have 1, 2, 3, 4. We have 4 identities. So if I know 3, I should be able to find the fourth one. For example, if we are looking for M2, if you are looking for M2, for example, here, you will rearrange the equation to what? You rearrange the equation by saying M1, all right, M1, V1, all right, this is V1 over what? Over V over V2. That's what I'll do to find M2 and any other equations. This is just like the density. We call these dilution dilution law or dilution equation. Dilution equation. We will be using that as well. So there are two what? There are two methods of determining molarity or concentration. M for molarity, you got to know which equation is appropriate. This is when we already have a solution with known what? With known molarity. We use this equation. But if we are starting with a solid reagent and we have to make a solution with a given concentration, we use the previous one, number of moles over volume in liters, number of moles over volume in liters. That's all what I want to know as far as the prerequisite skill is concerned. You can find, all right, you can find the PowerPoint slide I'm sharing with you, okay, on module 4, experiment number 8, experiment number 8. I don't want to waste my time. We'll come back to this slide later on, all right, when I get to the point where it's called for using spectrophotometer. Let me just real quick show you the data sheet, all right. This is the data sheet, and you need to fill in, of course, your name, all right, the section and the date. There is no way, listen, there is no way you will fill in this table 1 or part A, preparing the stock solution. Stock solution is the solution which you will use for the entire part of the experiment. Think of it as the one you always collect from the fume hood, and then you take to your workstation, and then you will use to carry on or perform the experiment. That's what you will be doing in part A. And now, in part A is we will prepare a stock solution with known concentration. Do not just dive into the data sheet and try to complete. It will call for watching or, all right, it will call for watching the simulation. All right, there is a simulation on posted on, all right, there is a simulation posted on Canvas. I want you to watch the simulation so that you collect the information you will need. Experiment number 8, this is the demonstration, and the instructor here will walk you through the experimental setup for part A. So weighing 100 ml volumetric flask. So that means you'll have to weigh that so that you do it. You get the mass of the flask. All right. You're going to get the mass of the flask, and the mass of the flask plus the stock, what? The stock sample. So once you know the mass of the two, you can find the what? You can find the mass of the stock compounds, mass of the stock compound.
We have 62.0772 grams.
So if I were you, I'll post a video, or I will stop. Like right now, I stopped the video, and I can record the mass of the empty flask. That's what you need to take note of.
And I have pre-weighed some copper sulfate here in the weighing board. It's a little over 3 grams. We will check that again once I get it all added here.
So with that, this is what you will do. Once you know now the mass of the flask and the stock compound, and if you have, it's talk about the copper sulfate, all right? Copper sulfate, you will need that to calculate the molar mass. So I will also I'll reconcile the top hat, the lab manual at top hat, and by the way, take correction of what we'll be using. It is not copper 2 hydrate, not hexahydrate, but this is the compound you will use. It is only not hexahydrate. So I'll let the mass of what? Copper, sulfate, and for oxygen, you add to get the molar mass of the compound we'll be using. And you'll get the note. This is the analytical wavelength. We will need that as well. So with that, I know the chemical formula of the compound or the stock compound. You can find, so the number of moles here, the number of moles for line 3 here is just, if I know if you have the mass here, number of moles here is given by the mass in grams, all right, of what? Of molar mass. And I just showed you the what? I just showed you the chemical formula for the compound. It is C U S O for subscript. There is a four subscript right there to give you the number of moles of what? Number of moles of the stock what? Number of moles of the stock compound. Now, to get the molarity here, you'll have to use what? This line 4 here, you'll have to use the number of moles, all right? Number of moles over what? Number of moles. This is the number of moles here of volume in liters. This is what you'll be doing, number of moles over volume in liters. You need that for line 4. And unless you read the instruction on top head, unless you read the instruction, you need to know what is the capacity or of the volumetric flask. What is the capacity of the volumetric flask? From the instruction at the top head, it's talk about the volume, all right? You need to read the volume. Look here. This is the key. What is the size of the volumetric flask? If you don't go back there, you will not know what volume am I using. So you have the volume in ml, volume in ml. So whatever he has here, this is the capacity. 100 ml what? 100 ml volumetric flask. What he's holding here, this is what is given in the procedure. With that, you should be able to calculate the molarity of the solution. Having calculated the number of moles in line 3, you should be able to calculate the molarity for line 4. That is the number of moles over the volume in liters of the stock solution, of the stock solution. Any question? Any question? Let me just stop sharing my screen. That's the only way I can see if someone has a question on the chat room. Let's see. Is the stock solution a combo of salt and yes, exactly. If I missed that, Margaret, it is the combination of that. It is the combination of distilled water and the stock compound, which you should have by then. Let me go back to the screen and walk you on how to complete. Where is the analytical wavelength? It comes from the data sheet here. If we are using what? We are using copper. This is the compound we are using to prepare the stock solution. And we have the analytical wavelength. That is what we'll be analyzing. What that means is the sample or the molecule or ions of the stock compound will observe light in the spectrophotometer. Spectrophotometer is just an instrument used to determine the concentration of the solution. So with that, I know the analytical wavelength of what? Analytical wavelength of the solution. That's what I need to see here. Okay, that's what I need. If it was in the lab, each team may have a different compound here, and then you have to use your assigned sample, but everybody will be working with the same one, same sample. Now, this percent transmission here, all right, you will observe again from this demonstration how he will perform the experiment and collect the data from the spectrophotometer. Spectrophotometer is simply, all right, is an instrument used to collect the percent transmittance or percent absorbance of a solution. You read this slide, see how it's used to collect the percent absorbance by placing the sample in what we call the cuvette. All right, a sample is placed in a symbol. You mean I had one here. It's transparent. Let me use my mask to see if you can see. In case you can see, that's fine. You may have a hands on down the line. Place it in the sample compartment, and here is the readout for either percent transmittance or absorbance. And if we know, all right, if we know either percent transmittance or absorbance, we can calculate the other. In this experiment, the data will be collected in percent transmittance. And going back to the data sheet, all right, going back to the data sheet, I will or you will see in the you'll see in the demonstration here that there will be some data you will collect for percent transmittance. You will observe the demonstration, record the percent transmittance, and you will calculate the percent ups or you will calculate absorbance, not the percent absorbance. By using this equation here, all right, there is an equation here which relates percent transmittance and absorbance from the background procedure here. This is the relationship between percent transmittance and absorbance. So you will take the percent transmittance 2 minus the log of percent transmittance, give you, and please, when you fill in the data sheet, say line 5, I'll say number 5 for calculation, plug in this equation first, and then key in the percent transmittance from this line, plug it in here. This is the equation you will use to fill in or to complete line 5. Is there any question on part A, preparing the stock solution? Preparing the stock solution. If there's no question, let me just stop sharing and see if someone has a question on the chat. See if there's no one has a question. And was the mass of the flask 100? And was the mass of the flask 100 ml? That is, yes, that's the mass of the empty flask. Margaret, that's the mass of the empty flask itself, and then the mass of the flask. So when you look on the data sheet here, this is the mass of the 100 ml flask. This is the mass of the 100 ml flask and the stock solution. So the difference between the two should give you the mass of the stock compound being used in this experiment. Now let's move on to part P, preparing dilution for generating a graph. Pay in mind, in part P, the data you will collect or the data collected already for you will be used to plot a graph using Excel. You need to teach yourself, or by now you should be able to use a spreadsheet to generate a graph similar to what you see here. This is the what you will come up with at the end of it for X part P. You will have a graph similar to what I do have. Where is it? Let me show you that graph. Your graph should look like this. This is the graph you will be looking at. You will include a trend line, equation of a straight line, y equals to mx plus b, where b here is, did I share my screen? Let's see if it's sharing the screen. Let me share my screen, show you the data you will grab. So this is what I'm talking about in part P. You will use the data in part P to generate a graph of observance versus the molarity of the solution, where, all right, the equation of a straight line, this will stand for, or this will be the molarity, x, I should have said x. Let me erase this right here. And say x is the molarity of the solution, molarity of the solution. When you generate this graph, y will be the observance, m will be the molarity, and x, no, m is the slope of the line. Here, m is the slope of the line. Understand what this means. This is right here is observance. No, it's on y-axis. Here is the slope, and you should get a slope value from your data. And then this one will be the what? Concentration or molarity. Let's say this is molarity. Or concentration, all right? This is concentration, sometimes this is concentration. And this is y-intercept. You know what equation y? Intercept. So if you want to find the molarity of a solution, if you want to find the molarity of a solution, you will have just to rearrange this equation to get the molarity. This one, you rearrange the equation, take p on the other side. That means it's gonna be y minus b over what? Over slope. All right, over slope. Over slope, all right, here, to get what? To get this is calculated what? Calculated molarity. Calculated molarity. We'll come back to this. Let me go back to molarity. Let me go back to part P. How are you going to generate the data in order to come back to this graph here? I will, let me save this. I'm just gonna save this. I already saved that. So from part, all right, from part P here, you will, from part P, you will have to read the top hat instruction. If I read part P here, you need to pay attention to, the volume you will need to take from the stock solution, and you take it to where? Remember, in A, you should know the molarity of your solution. From part A, you should know the molarity. This is your M1. This is, all right, take note of this. This is the what? This is M1 here. For a minute, we call this M1. We're gonna use this in part P. So that in part P, or to complete that table right here, you'll have to do what? The instruction here is clean 50 ml volumetric flask, 4 of them. So you're gonna have number 1, number 2, number 3, number 4. Rinse with the iron as water and you label to 1, 2, 3. It will correspond to this. It will correspond to 1, 2, 3, 4. So you know the capacity. Listen, you know the capacity of the volumetric flask. This is your M. This is your M2. All right. And refer to the table 2. Use the technique clean that's fast and the pipette. You need to know how many ml of the solution will be done. So in other words, we will fill in this table right here based on the solution, and the instructor did the work for you, and already the volume is filled up. All right. Yes, you'll turn in the graph. I'll come back to that. So excuse me. For part P, this is the data already filled for you. You see this? For part A, we already have the data here. This is the mass of the flask. This is the mass of the flask and the solution. This is the analytical wavelength, and this is the transmission. You ask us to do the calculation. Now, for part P, this is the data for part P right here. 5 ml of the stock solution, 10 ml of the stock solution, and the 20 ml of the stock solution. You will use the molarity equation or dilution equation to use the to fill in the molarity here. Here, you'll have to use the molarity equation. Right here, this is what I'll use. M1, all right, M1, V1 equals to what? M2, V2, all right? Your M1 is all what you have here, all right? Your M1 will come from here, from part A. M1 is from part A. By this time, you should know the molarity of your stock solution. That will be your M1. V1 is this. V1 will be this for each run. You see this? For each run. For each run, it's gonna be like that. M1, V1, V1, V1 for flash squad, you know V1 for flash 2, you know V1 for flash 3, you know V1 for flash 4, you know V1. M1 will be constant for all of them. V1 will be changing from flask to flask. Now, M2 is what you will be looking at. This is M2 right here. This will come down here is what you will be looking at. This will be here, all right? This will be M2. This will be M2 like that. That's what you will be looking at. And if you rearrange the equation, all right, M2, all right, M2 should be what? M2 equals to M1 V1 over what? Over V2. What is V2? Somebody just tell me what is V2.
50.
Thank you, Jose, right?
Yep.
Thank you. Yeah, V2 is 50. And it's gonna be 50 for all of them because you are diluting it to 50 ml. So with that, you know the molarity of your what? The molarity of your diluted solution. Already here, Look, already the observance values has been collected for you. You'll have just to fill in the data sheet. Please use this slide on PowerPoint to fill in the information you need for part P right here. Let me just pull, all right, pull the data sheet here for part B. The percent transmitter has been filled for you, and I think I can just clear everything here real quick. So molarity is from M1, V1, M2, V2. The one I was just showing you here, that you use M1, V1 equals to M2, V2, and then you make V2 the subject of the formula. Remember, V2 is 50 ml. V1 was the 5, 10, 15, and 25. And then M1 is from the stock solution. This is coming from the stock solution up there. It's gonna give you that. Percent transmittance is given. Percent transmittance is given. It's already filled for you. Now, you need to calculate this. You need to calculate this from this line 7 here. Line 7 here, you have to use A. This is calculated observance equals to, remember 2 what? 2A minus log of what? Log of percent T, percent transmittance. So you should know the percent transmittance, you already have those values where? You already have those values in the PowerPoint slide. You'll have those values in the PowerPoint slide. Yeah. All right. So it's gonna give you the calculated. Remember, this is calculated what? Observance. You are calculating the observance. Now, dilution factor here is you need to go back to the, it's assumed that you have read the background. I should have erased the, I'll clear everything here so that I'll walk you through how you're going to calculate the dilution factor. You need to read, come here, there is a dilution. Dilution factor is given by this equation, is the final volume right here. Total volume, all right, over the original. And please show me the calculation. What I mean here is total volume for all of them was 50 point what? This was diluted to 50.0 ml. Remember, each solution was diluted to 50 ml, 50 ml, 50 ml, 50 ml. But the original here was firing as 5, all right, 10, it was going to 15, 15, 20, and lastly 25, and lastly 25. This is how to find the dilution factor. It is the total volume. All solutions were diluted to 50 ml, and the original, the stock solution varied from flash number 1 through flash number 4. So that's what I'll do, or use that equation. Let me just clear that before I switch on to the data sheet. So dilution factor here, you'll have to use the stock solution volume and calculate the dilution factor for that. Any question on dilution factor? Remember, total volume was constant for all of them. They were diluted to 50 ml. 50 ml. All right. So if I know to generate a graph similar to this, before we go to part C, let's go back to our graph again here. To be clear, Margaret, watch this. You had a question about the graph. So if I know, all right, if I know so far I know the calculated observance here, and you know the molarity here, you will plot the observance versus the molarity. Molarity on the y-axis, I mean on the x-axis, and observance on the y-axis, so that you have something similar to what you see here. And please draw to scale. I don't want a very tiny curve on the, on the corner. And please observe on the guideline, you should have the title. You should have the label y-axis. You should have to label the x-axis with the appropriate units. So this is the molarity and then the observance, and include the equation of a straight line. Include the equation of a straight line, so that you will use this graph for part C. And remember what I said here, to repeat myself here, molarity is the same as X. X is the same as calculated what? Calculated molarity. So each time you'll have to plug in this observance here. Let me just go back here. How are you going to make use of your graph to complete part C here? Let's go first of all to PowerPoint slide. We have to toggle between PowerPoint slide and this part right here. Let's see. I want to show you what you need to fill in from the PowerPoint slide here. For part C, you have experimental percent transmittance for solution A, percent transmission for solution P, for solution C here. Percent trans, you have the values here. These are the values. These are the values. These are the values for part C. So if that is the case, you'll have to fill in this data sheet right here. You see, for part C, experimental percent transmittance. For solution A, it is right here. For solution B, it is right here. For solution C, it is right here. You got to fill in these values here, here, and here from the PowerPoint slide. From the PowerPoint slide information here. This is for A, percent transmittance for experimental. You see here, experimental. That's how you will start completing part C. And then experimental calculated observance. So if I know, look, if I know the observance from here, you will use this equation from line 9 here. Calculate experimental observance. A will be here. This is what you will do for all experimental. 2 minus log of what? Log of percent T. This is what you will do for A, P, C. A, P, C. Experimental calculated observance right here. If I know percent observance for solution A, P, and C, I'll use the same equation for, let me move this so that you see, this will be applicable also to experimental calculated observance right here. Gonna do the same thing. You'll do the same thing for this right here. That's how you will calculate experimental what? For line 9, line 13. Once you know the percent transmittance, which you already have the values, you plug in there. Now, from the graph, from this graph right here, it won't allow me to switch unless I cancel that. This graph right here, you will calculate what? Look at the question again here. It's asking you experimental experimental molarity of solution A calculated from the fit of the data. When they say fit of the data, this is just the equation of the straight line. I see a student, they get stuck or they don't even realize that they are at a loss and they submit their work without the graph, and then they also even make it worse, they don't feel anything because they don't know. So you need to generate a graph. Once you have a graph, you will use the graph to complete line 11. How are you going to complete or calculate that? So observance from the equation of a straight line, if I know the molarity here, from this equation here, from the graph, experimental molarity, this x is the molarity. X right here is the molarity. I intend to complete that. So I wanted to say here is the molarity. This is the molarity. And it is given by, that is x, it is given by A, which is the observance value, minus B, which is a constant of the straight line over what? Over 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 the slope of the line, over the slope of the line. I mean to say slope of the line. I'm looking for my graph right here. So the slope of the line is M, X is the concentration, and then we divide, you divide that by the concentration. That's what I'll do, divide by M. So how is it going to vary from, how is it going to vary from solution? So if I know the observance from, let's say solution A here, let's say solution A, we know experimental calculated observance. So if I know observance for solution A, I'll plug it in here. I know the y-intercept from the slope of the graph, and I know the slope of the graph. The slope of the graph, this is constant, this is constant. This will vary from solution APLC. That will give you experimental molarity from the experimental observance. So if I know observance for solution A, observance for solution B, observance for solution A, this will change from A, B, C. This is constant, and then I get what? You get the molarity of all of them. Now, for percent error, you see here, percent error, all right? How are you going to calculate the percent error? Experimental molarity versus the calculated molarity. You will have calculated the molarity from here, and the experimental molarity. The absolute between the two, let me just use the equation here. Maybe it's gonna help you out. For this part right here, uh, take the absolute value of experimental minus the calculated, whichever is, you know, calculated molarity, whichever is small, it should turn to positive over calculated. This is calculated right here. And then time is what? Time is 100 times 100%. This is 100. It's hard to write with my finger. So that's how I'll calculate the percent error, comparing the calculated molarity versus experimental molarity. All right, percent error versus molarity. That's how I'll do for, and here is absolute. You know, absolute just to make it positive, depending on which one is correct. Over calculated time is 100. This is the equation you will use to calculate. You may not see this equation, all right? You may not see this equation in the handout or in the top hat because they expect you that you have learned elsewhere. Just like the molar mass concept I walked you earlier on through, you are expected to have learned somewhere how to find the molar mass of a compound. You will not see the steps of calculating the molar mass in the procedure for this lab, but because it's a concept you should have learned elsewhere, they expect you to recall and use in moving forward. Likewise, for this percent error, we did the percent error before. Percent error will come down the line. Other than that, it should be straightforward. That is all what I wanted to walk you through before we take the quiz. Let me stop sharing my screen and go back to the chat window, see if someone has a question. Margaret, are we going to turn the graph in with? Yes, you'll attach everything for this lab to your uh, data sheet. The graph will be attached to the data sheet as well. Hope that answers your question. Any other question?
Yes, I got one real quick.
Yes.
When we do our N1 V1s equals N2 V2s, our volumes are to be in liters, correct?
No, it doesn't have to be in liters. You don't have to.
Okay, you can do it straight in milliliters as well.
Yeah, use ml. It's much easier and faster. Any other question? So I received a couple of emails regarding the pre-lab for this lab, and I hope what I went through will help you in also answering the pre-lab questions. Pre-lab questions. I will make the quiz available right now. It is around 1:55 for 30 minutes. So around 2:30, you should be done with the quiz. I'll be available on Zoom. Should you have any question, just send me a message and I'll respond. Just get ready, have a calculator, a scratch paper, periodic table, okay? And I'll make the quiz available in a few minutes. Thank you for tuning in this afternoon.